So this is going to be a video on the first chapter, first lesson of geometry, and we're just going to cover the basics. This is mainly going to be a terminology type lesson where we go over the basic terms that we're going to be using and sort of defining the key concepts that we want to use. So we'll first start with the basic word of geometry. So kind of what are we going to be studying here in this lesson or this course? So geometry is a Greek-derived word, comes from the word geo, meaning earth, and then metry is derived from meter, which means to measure. So geometry is sort of earth measure or measuring the earth, which again, in Greece, where it was mainly focused and studied in the early days, they were talking about, again, how to measure and figure out the stuff that interacts in their world. And thus, we have to use a lot of shapes and figures and ideas and stuff that can be manipulated with physical properties. So it's not just about shape, but it's more about the relationships that shapes have with each other. So points, figures, lines, again, excuse me, not things that you might think of as shapes necessarily, but all those basic ideas of, again, points, lines, figures, planes, and how they intersect with, with each other. So again, compared to algebra, geometry is a lot more visual and spatial, but we use a lot of Algebra 1 topics in geometry to sort of um, define and calculate certain features. So the geometry we're going to be studying is Euclidean geometry. So when most people talk about geometry, they're assuming Euclidean. There are different kinds of geometries. Euclidean is probably the most common one just because that deals with objects that are on a flat plane, which for us, granted that we are on Earth, which is a spherical shape, because of size and relativity and whatnot, most of the stuff we deal with in everyday life is based on Euclidean geometry because we walk on a flat surface, technically speaking, because we're so small it appears flat to us. Therefore, Euclidean geometry applies to it. But again, for example, most of the basic things people talk about, like all the angles in a triangle add to 180. So if you don't know this geometric property, which you probably learned in Algebra 1, if you have a triangle, then this angle plus this angle, these will all add to 180 for every triangle. All the angles in a triangle add to 180. That's not actually quite correct though, because if you want to make a correct statement, you would say that if a triangle is drawn in a Euclidean space, which is a flat plane, like a piece of paper, then all the angles would add up to 180. But because it's a bit of a mouthful when you're first starting math, we just say all the angles in a triangle add to 180. So basically what this is saying here is that if I have a sphere, like if I have a ball and I draw a triangle on this ball-like shape, all these angles would not necessarily add to 180 because the triangle itself would be curved because I'm drawing it on the surface of a ball, not on the surface of a flat plane. So when we talk about stuff and rules in here, we're always going to be assuming Euclidean geometry. So we're not necessarily going to say this part here where it has to be drawn in a Euclidean space. We're just going to say it like this, the easy way, because again, most of the stuff we're going to assume is Euclidean. So just to give you some perspective a little bit before we kind of focus in on Euclidean, the reason it's called Euclidean is because it was kind of developed or started by a guy named Euclid. He was a Greek mathematician. And most of his properties and stuff deal with flat plane geometry, so we call it a Euclidean geometry. But there are other types of geometry like spherical geometry, which is geometry that's when you're drawing stuff on a sphere. Like again, for a triangle, if you draw a triangle on a ball, all the angles will actually add up to more than 180 because each line is curved, so to speak. And then this is called a hyperbolic geometry, where you're dealing with drawings that are on kind of a folded in space. Not quite a sphere, but kind of like a saddle, it says there. So these do have their place. Again, spherical geometry is kind of important because, again, we're living on a sphere. So if we're doing grand, big things like space and whatnot, spherical geometry becomes a little bit important there. Again, airplanes flying, that takes spherical geometry because you're covering a curved distance when you're going that far out. But again, for us and our properties in this high school class, we're going to be focusing on Euclidean or flat plane geometry. So just a brief sort of overview about why this specific one that we're using here rather than the other two. Although hyperbolic geometry is kind of wacky if you ever get into it. So getting more into Euclidean stuff here. Again, it was developed by a guy named Euclid. He was a Greek mathematician, as I said. He developed a lot of theorems and a lot of postulates. So a theorem is basically kind of like a rule that we know is in geometry. It's like all the angles in a triangle add to 180. It's a theorem. Interior angle sum theorem is what it's called. And it's actually a book. It's a book of basically all his stuff there. So Euclid had a book called The Elements. Obviously, he didn't name it The Elements when he was writing it. It was Greek after all. But it's been made into this book here, and it's just a bunch of proofs, just a bunch of stuff saying, hey, this is true and here is why. So it's basically a bunch of this is true, this is why, this is true, this is why, this is true, this is why of math. And it's built as kind of a stepping stool there. So it starts with a very, very, very few amount of assumptions. So when he was writing this book, he's like, I'm going to assume the least I need to assume. So for example, going back to the triangles here, all the angles in a triangle add 180. He didn't assume that. He had to prove that. He said, okay, without assuming that, how do I know it's true? How do I know that all the angles in a triangle add 180? How do I know that I can draw a triangle on a flat plane even? How do I know that even drawing a triangle is possible in a certain amount of space? How do I know I can draw a rectangle or a square? Stuff like that. So this is an example of kind of how his proofs were written. Obviously, again, it was in Greek, but this is an excerpt from his book here. And it's proving that if you have a line segment, you can draw an equilateral triangle from it. So if I draw a line AB, I can make it into a triangle with 3 equal sides. And again, for us that might seem trivial, like, well, duh, if you have a line, you can draw 2 other equal lines to make it a triangle. But again, he didn't want to assume that. He wanted to prove that, to prove it was possible every single time. And that's his proof of it. And again, this was way back in Greek times, so they didn't have stuff like a calculator or even marked rulers. They didn't have a ruler like 1 inch, 2 inch, 3 inch. They had a sort of measuring stick, I guess, where they had a piece of stick that they could use over and over again and kind of act like a ruler, but they didn't have rulers in the sense that we do here. So again, it was very limited stuff there, and he was able to derive quite a bit of things there. Algebra has its version of this too. It's made by a Persian mathematician. This was his, excuse me, this was his name here. I'm not even going to try to pronounce it. But the book was called this, again, this statement right here, but it's this word in the title that was kind of shortened to. So this was the entire title of the book, this entire phrase here, and it just got shortened to algebra as it moved down in time there. But that is the algebraic version of Euclid, essentially. So algebra has its own little book of theorems and stuff where it started as well. So let's go over some basic terminologies that Euclid uses and that we're going to be using. So a point is a sizeless, shapeless dot, so usually labeled with a letter. So this would be point A. Again, even though it looks like it has space, a point in our sense does not take up any space. It's just a formless, shapeless void in the ether that we're going to designate essentially. So this is not a circle, this is a point. It has no mass, it has no shape, it has no width, it has no height, it has no area. It's just a empty space in the ether, in the area. A line is when you connect 2 points. So a line is when I have 2 points like A and B, and I connect them. Now a line has length, so you can well, a line segment technically has length. So a line goes on forever, so it has an infinite amount of length, but it has no thickness, so it does not have an up and down measurement. Essentially, it only goes left to right. Or again, put another way, that there is no, well, yeah, that's the only way to say it. There is no thickness to this direction here, to this line here. So it has a length in terms of you can stop and start it wherever you want. It goes on forever by itself, but you can designate points where you want to start and stop, but it does not have a width. And a line is only going between, or sorry, there's only one line between 2 points. So if I have the point AB, there's only one line that goes through those. And usually we call it like this. So that's how we designate the line AB. We say AB and then we put the line symbol over it. So that's how you call out a line AB. A plane is basically an infinitely long and wide flat surface that's made up of points, as it says there. So basically a plane is like a slice of space. So if you take a piece of paper and you imagine it going on forever in all directions. So here's my piece of paper. Imagine it going on forever this way, on forever that way, on forever this way, and on forever that way. And that's what a plane is. So it's a slice of space, essentially, or basically like a two-dimensional line, so to speak. It's a line that goes left and right and up and down, or front and back and side to side. That's what a plane is. And a plane exists always between 3 points. So if you have any 3 points, there's always one plane that goes through them. Not three, but one plane that goes through them, as long as the points are non-collinear. And non-collinear means that they don't fall into a line. So if I have the points A, B, and C, those are collinear points because there's a straight line that goes through all three. So a non-set of collinear points would be like this over here. These 3 points are not collinear. Therefore, there's only one plane that goes through all 3 of them. Now, there's more than one plane that I can draw, but there's only one plane that includes A, B, and C. And usually a plane is designated with a letter like here in the top right. So we'd call this plane M because that's what the letter is. Or we could even call it plane ABC. So that would be another way to designate a plane. It's just label it plane and then write out 3 points in it. We don't really have a fancy symbol for plane. We just say the word plane and then we write down either the 3 points that are in it or the letter in the top right that it's designated as. So we've talked about a little bit of these terms already, but collinear and coplanar. So collinear points are points that lie in the same line. So in this case, B, D, F, E, and C are all collinear. So we could call this line FC. We could call this line DC. We could call it line BF. We could call it line DE. So we could call it a bunch of things. So when you're labeling a line, all you need are 2 points on it, but there might be more. You could also label it as a lowercase letter. So in this case here, I could also say line F, uses a lowercase letter or a cursive letter. But sometimes if you have a line in like a big picture, they might just label the line with a single letter rather than having you pick out 2 points on it. Now, if I put like a point here called X, X would not be collinear with all the rest of these. X could be collinear with B because I can draw lines between them, and it could be collinear with D, but it's not collinear with both D and B because I can't draw a line that's straight at least between D, B, and X. So in order to be collinear, a straight line has to go between all the points involved. So B, D, F, E, C are all collinear, but X is not collinear with all of these. It can be collinear with one at a time, but you can't say B, D, F, E, C, and X. X has to be its own collinear with just 1 point at a time here because of its position. And then coplanar is just the same thing, but it's just on a plane. So F, J, H, G, and I would all be coplanar. A point that would not be coplanar would be like something like X here. So if this is point X is kind of above the plane. So here is the bottom, and X is kind of floating up here. So X would not be coplanar with these points down here. And you can also have lines that are coplanar. So like a line FG and line HJ would be coplanar. A line FH and line GH would be coplanar, that sort of stuff. So as long as they're in the same plane, they're coplanar. As long as they're in the same line, they're collinear. Excuse me, just clear my throat there. So let's go over some problems here just to practice. So it says use the figure to name each following. A line containing W. So the line can be named as line N or any 2 of the 4 points that can be used. So this is an example of one they already did here. So they want a line that contains point W. Well, all of these lines here contain point W. These especially because they have W in them. So VW obviously contains W. WX obviously contains W, and so on and so forth. You could also say line N. They didn't put this down there, but you could say line N because that also contains W. You could say, as they say here, line VY, because line VY goes through W, so it also contains W. So again, there's a bunch of different lines that contain W. As long as the line goes through W, we can say contains it. So let's do kind of one on our own here. So let's do 1A here. It says a plane containing points T and Z. So give us a name of a plane that contains points T and Z. So I want T, I want Z. In order to be a plane, I need to have at least 3 points. That was the rule we had for planes, right? Let me try and make that T a little bit better there. Whoops, don't want that. That's the one I want. So if we go back a little bit, remember a plane contains 3 points at least. A plane needs at least 3 points. So if I pick another third point down here, that would be a plane containing points T and Z. So 1A. So for example, I could say plane T, Z, X, because those would be three non-collinear points. T, Z, X. That would be a plane. Again, it's just basically naming 3 points, make sure you include T and Z. Another plane I could say would be, whoops, get back to my pen here, would be plane T, Y, Z, because still I have T and Z, therefore it's a plane because it has 3 points, and it still contains T and Z in it. So basically any plane you want, as long as T and Z are involved in the naming of it, we're good. What about a line containing point T? Well, a line that contains point T, you could say, again, any line that has T in the naming of it, so like line TX, this right here, TX, that'd be a line that contains T. You can say line TZ, although it's not shown, technically speaking, there is a line that goes through T and Z. You could name that. Because again, it's not shown, but we know by a rule, go back here, sorry, my mic cuts off for some reason. So if you hear that go off, that's my bad. Just give me a second to turn on. But remember, a line is a one line between any 2 points. So as long as you have 2 points, you have exactly one line. So even though they don't show it here, but I know that because T and Z are 2 points, there is a line that goes through them. You could also say like line R, because remember line R is this entire line here. Line R is this entire line. So if I just say line R, then that includes also point T as well. But any line, again, any 2 points that has T in it, that's a line that contains point T essentially. All right, so intersections. So when you have 2 figures that intersect, they usually intersect in a few ways. So when you have 2 lines that cross or that intersect, they intersect at a point. So when they cross, they form a point. Like right here is point J. So when line F and line G intersect, they make a point, and that point is called J. Or you can say when line FG intersects line IH, makes point J. Now when you have 2 planes, so think about 2 pieces of paper that are kind of, one's going through the other. So 2 pieces of paper, one paper is going through the other. That's 2 planes that are crossing. They form a line. So like here, you have this plane, this piece of paper, and you have this piece of paper here. And then if I erase that to give it a little bit better picture now, when you intersect them, they make, let me try to get a different color here. There we go. They make this line right here. So that line is the intersection of the up and down plane and the left and right plane essentially. So it's kind of interesting to note that basically when 2 things intersect, at least for now, they make an item that's 1 dimension less than they are. So when 2 lines intersect, they form a single point. So 2 lines, again, a line has a length, a point does not. When you 2 planes, which are 2-dimensional, because a plane has a length and a width, they make a line, which is 1-dimensional. So that's one way to remember, is that they always intersect at 1 dimension less than what they already are. Lines are 1-dimensional because they only have a length. Points are 0-dimensional because they don't have anything. Planes are 2-dimensional because they have a length and a width. But if you just remember the idea here, then again, it's not that hard to remember here. When 2 lines cross, they make a point. When 2 planes intersect, they make a line. So space is what we call a defined term. So a defined term is basically a term that is described using undefined terms. So line, point, figure, plane, those are undefined terms. Those are terms that we can't really put a definition on in geometry. We have to use examples or figures to demonstrate. Space we can define using those terms. So space is defined as a 3-dimensional set of all points. So points, undefined term, is used to define space. So space is a defined term because it's using the word points in its definition. But space is this, again, goes on forever, left, right, up, down, front, back. Space is a 3-dimensional area that contains all the points in it. Come on. There you go. So let's, again, try to identify some basic geometry figures here. So we're looking at this picture up here. And let's do some of the guided practice down here. So we'll do 4A. So it says are points E, D, F, G coplanar. So let's figure out where they are here. Let's highlight them. So our point's E, D, F, G coplanar. Well, here's E. Whoa, let me try to get my highlighter actually, rather than that. Highlighter, and let me do it in green color here. So here's E. That doesn't really look well. Let's do yellow. That's not that much better, so we'll go with it. Here's E. Let me actually do. Sorry, I'm trying to find a good color here. That's better. So there's E, D, F, and G. Are they coplanar? Well, not quite. E, F, G are coplanar, but D is up here, and it doesn't quite line the same plane as E, F, and G. So in this case, we'd have to say no. D is not coplanar with the rest, so no, they are not coplanar. Again, in order to be coplanar, all of them have to be in the same plane. If one of them isn't, then the entire thing is a no. And then 4b says at what points, so 4b, at what point or in what line do planes JDH, JDE, and EDF intersect? So again, let's try to figure out if we can't draw that out here. So let's get my highlighter again. At what point or line do planes J, D, H? So here's J, here's D, here's H. So JDH is kind of this space right here. This is going to get a bit messy. So JDH, JDE. So JDE. So that's this sort of green triangle in the back there. JDE. And then EDA or EDF. So EDF. Let's highlight that here as best we can. EDF is right here. So at what point do those three planes intersect? Well, if you look here, they have a common letter, right? If we get my pen here, JDH, JDE, EDF. Well, if we have three planes here, it looks like they intersect at the point D. They don't really intersect in a line, and that's because they're not just two. If I just had two planes here, then I could say they intersect in a line. So like JDH and JDE both intersect. Well, where do they intersect? Well, they intersect at line JD. JDH, JDE. Again, it's in the name. But because I'm dealing with three planes, they don't really intersect in a line. They intersect more into a point. And again, in this case, the point that they intersect at is point D. And one way to know that is by their labeling. They each have a D in them. Therefore, that has to be a point where they all share. So they have to intersect at least at point D, if not in a full solid line, which again, they don't, unfortunately. But again, that's because they're arranged that way. So use the labeling to help you out there. So for example, as a side note, if I said, give me the figure where plane, let me here. So I say we have plane. Whoops, lost my mouse there. Plane. This is not concerning this figure here. So ignore this for a second. If I said we have plane E, D, F, and we have plane E, J, F, and I said find out where they intersect. Well, I know just by the name of it, by their name here, we have E, D, F, E, J, F. Well, because they have the points E and F in common, that means that these are both going to intersect at line EF. Because if they share 2 points, that means they share a line, because remember, a line is between 2 points. Therefore, they're going to intersect at line EF. So use the labeling of the items there to help you figure out where they're going to intersect, because that can sometimes help you, especially with planes there. So the common letter between all the planes is probably the letter that they cross at. So that's it for this video. Again, basic terms here. It's a little bit weird at first just because these terms are terms that you're used to just assuming you know what they are, because again, you're defining a line. Like, who doesn't know what a line is? But that's kind of where we start in geometry. We go to the very basics, the very root of stuff. We sort of get down to the bare bones of it, and then work our way up to the more steadier or more complex concepts there. So we're going to be starting with the very basics here and kind of digging in deep, which is going to be a little bit weird at first, but it will all iron out in the end as long as you stick with it. That's it for this video. Have a good day.